I'm not sure what happened to that video. I think I pushed the wrong button and I stopped recording instead of switching over to talk to you. So, where we were was we were saying that you can plug in any concentration of NO2 minus, you can plug in any concentration of NH4 plus, and the rate law will always work, right? And so, to switch this back, let's see if I can do this. Ha, success. If you switch, if you put in any value for NH4 plus and any value for NO2 minus, because this rate constant, this K value will always be the same, we can now calculate what the rate of our reaction will be no matter what concentration we start with. We don't have to necessarily set up the experiment and measure the change of concentration over time to figure this stuff out, right? Which is actually really nice. So experimentally, right, we don't have to go set up a million experiments anytime we want to know the rate of a reaction. We can set up 3 or 4 experiments, change the concentrations of our starting materials, and kind of get a sense of what is the overall um, rate law for this reaction, right? So if the rate law depends on NH4 plus concentration and it depends on NO2 minus concentration, we can calculate, well, if we want our reaction to go this fast, we need to put in this amount of each one of these things in order to get there, right? And this is going to be really important when we get to equilibrium, but we're setting it up for now. Now, it won't always be this nice one-to-one relationship between these two. And so I want to do an example where we look at something that isn't like, it's not always going to be double the concentration, double the rate. That would be too nice and too easy, right? So let's look at the next, I found the wrong thing. Let's look at this example, right? So we have A plus 2B goes to C and D. If we double the concentration of A, the rate stays the same. And if we double the concentration of B, the rate is quadrupled, right? So what does this say about A? It says that the rate is constant, right? So there is no concentration of A. The concentration of A doesn't affect the overall rate, right? So if the rate stays the same as you change the concentration of one of your components, then the rate law for that component is just the rate equals K. In the second case, our rate is going to be some constant times. In this case, since we double B and the rate is quadrupled, that means that we're going to need an exponent in this case. It's going to be the concentration of B squared, right? And so we do the same trick. We take these two equations and we combine them and we get the rate equals K times the concentration of B squared. And remember, when we combine K's, we just get a new K. So we have our rate constant here, and then we have the concentration of B squared here. Right? And so in this case, if we change the concentration of B just by a little bit, we get a really large change in the overall concentration of or if we change the concentration of B a little bit, we get a large change in the overall rate of the reaction. The rate law, or the instantaneous rate, the initial rate changes uh, by an order of 2. Right? There's a couple of things I want to make sure I point out. One, in every rate law, no matter what the concentration units are doing, the K value is the same, right? Or the K value will be the same for that reaction. So if we set up another reaction of NH4 plus NO2 minus and we make N2 and H2O, if we calculated K for this particular instance over here, as long as we're talking about the same reaction, the K value will be the same for the next reaction, right? Because that's a rate constant. Now, if we change reactions, of course, then all bets are off. If we go back to C4H9Cl plus H2O, right, that is going to have a different rate constant than the NH4 plus NO2 reaction. But every time that we do CH4H9Cl plus H2O, we're going to get the same rate constant. So we can use it to talk about other instances of the same reaction. We can use that K value to kind of to still to give us information about that. And same thing here, right? It's a constant. And so whenever we see whatever A is, whatever B is, whenever we see A plus 2B, we know what that rate constant is, right? Or hopefully someone has already done all the work, right? They figured out the rate constant and they've published it somewhere, so you can look it up and just have your K value, and away you go, right? So we're going to get to that when we do acids and bases. People have done those over and over again. So we have all those K values, and so we can just look them up in a table, plug them into our rate law, and away we go, right? Which is great. Okay. Oh, reaction order. Reaction order is actually very easy. So we'll talk about reaction order real quick. the order of a reaction is basically the exponent, right? It's the exponent of the concentration term in the rate law. Right? So if we have something that says the rate is some K value times the concentration of A times the concentration of B squared, right? This is first order in A, right? Because A has a exponent of 1, right? We don't write in exponents of 1 because there's no reason to. But if you don't have an exponent, right, then that term is first order in A. It is second order in B, because of course there's a 2 there. And if there was a C in this reaction, we would say it's 0th order in C because C is not part of the rate law. Right? So we can have first order in A, second order in B, and then we would say overall, this is a third order reaction. Because we add up the orders. So add up all the exponents. And so we get 1 plus 2, which equals, get out my calculator, pretty sure that's 3. Okay. So we add the exponent, the 1 exponent from A, the 2 exponent from B, and we get the overall order of the reaction. And so we can have reactions that are first order reactions where the first order reactions are the most simple because it's just the reaction is dependent on the concentration of one compound. And if that compound is doubled, the reaction rate doubles. If that compound is tripled, the reaction rate triples, right? That's first order reaction because you get a 1-to-1 mixture. They can be overall second order. So we saw an example of 2 different kinds of second order reactions, right? We saw the NH4 and the NO2, where we have two components that are each first order. Add them together, and we have the overall concentration of the, or overall order of the reaction is 2, right? So the second order reaction. Or you can have the rate equals K times concentration of whatever squared. That's also a second order reaction, although it's a little bit, it gets there in a little bit different way, right? So you have second order overall reactions. You can have third order, right? You can go all the way up to whatever number you want, right? Hopefully, most of the time, we're not going to go past third order. Most reactions, if you're a third order reaction, that means you have to have 3 different molecules come together to react, and at that point, you're kind of pushing against the bounds of probability. So we're going to look at, in the next video, we're going to look at first order reactions, second order reactions, and first order, second order, and 0 order reactions. And we're going to do some calculations on them. We're going to do some calculus, which will be fun. And then we'll get new rate laws that are even more useful, right? So all the stuff that we've talked about so far is set up for this next video where we get to the actual really useful rate laws. So stick around. You won't want to miss it.